Hey everyone, and welcome to another Explainer. Today, we're turning the clock way back to dig into a 2.4 billion-year-old geological crime scene. We're going to explore a period in Earth's deep history that literally altered the trajectory of all life.
So here's a wild thought. We normally think of oxygen as the essential breath of life, right? It's the very thing that sustains us. But what if its sudden arrival on the scene was actually highly toxic to the established early Earth atmosphere? What if early microscopic life accidentally set off a chain reaction that almost completely killed off everything it eventually nurtured? Let's dive right in.
Section 1. The Ultimate Climate Disaster. To really wrap our heads around this mystery, we first need to grasp the sheer magnitude of the catastrophe we're talking about.
Now, we aren't just talking about a bad winter or even a regular ice age here. We are talking about the Methane glaciation. This was a low-latitude planetary-scale deep freeze, a true snowball Earth. According to the geological records, massive ice sheets extended all the way to the equator. Basically, the entire planet turned into a giant reflective ice cube spinning in space. And that begs a massive question. What could possibly possess enough power to break Earth's climate that drastically?
Section 2. The oxygen suspect. Well, every good mystery needs a prime suspect, and in the case of this extreme, planet-wide freeze, our main suspect is, strangely enough, oxygen itself, specifically the very first biological generation of oxygen.
When we map out these staggeringly deep geological epochs, a really suspicious pattern emerges. Sure, there was an earlier freeze, the Pongola glaciation, way back at 2.9 billion years ago. But the cluster right in the middle is what we care about. The Great Oxidation Event, which is when atmospheric oxygen began to rise permanently, sits right next door to the Meganian Snowball Earth. You have to wonder, is that just a coincidence? Or are we looking at a direct cause and effect relationship?
The crucial evidence comes from a model proposed by Kopp and his team, showing how early cyanobacteria might have fundamentally broken Earth's climate. Think of early Earth as being kept warm by a thick, cozy greenhouse blanket of methane. Then, microscopic cyanobacteria mutate and start producing oxygen through photosynthesis. That highly reactive oxygen hits the atmosphere, reacts with the methane, and absolutely shreds it. The blanket is completely ripped away. Without that methane greenhouse effect keeping things warm, surface temperatures plummeted on timescales as short as 1 million years. And just like that, global glaciation begins.
Section 3. Competing theories and timelines. But, science is rarely that simple. For years, researchers fiercely debated the actual order of these catastrophic events.
It's incredibly difficult to prove the timeline when your evidence is buried in billions of years of compressed rock. We have to look closely at the counterarguments. Was it the chicken or the egg? One side argued that cyanobacteria evolved, pumped out oxygen, and caused the snowball. But the other side argued the exact opposite. They proposed that some massive astronomical or tectonic event caused the deep freeze first, and the extreme environmental stress of living on an ice planet actually forced early life to evolve oxygenic photosynthesis just to survive. And the debate doesn't stop there. We also have a fierce argument over the severity of the freeze itself. We've got the hard snowball theory up against the slush ball model. As research by Crowley points out, if the Earth was a hard snowball completely encapsulated in miles of thick ice, sunlight couldn't penetrate the oceans. That means photosynthetic life would have been halted entirely, which directly conflicts with the fossil record of early algae actually surviving this era. So the counter theory is the slushball Earth. This is an oasis solution, suggesting there was still some open water at the equator, but critics quickly point out that a slushball model really struggles to explain how a glaciation could last for millions and millions of years. It's a massive puzzle. To untangle these conflicting models, geologists essentially have to play matchmaker with ancient, messy rock layers across completely different continents. Imagine comparing stratigraphy charts from South Africa on one hand and Canada on the other. Researchers have to match up these incredibly old layers of glacial deposits, volcanic ash, and iron to piece together a global timeline. Because think about it, if the glaciation in Canada happened before the oxygen markers in South Africa, the whole oxygen caused the ice age theory completely falls apart. They desperately needed a definitive global timestamp.
Section 4. The isotope smoking gun. To finally settle this debate, researchers turned to chemistry, searching for an undeniable geological timestamp.
And they found it. Now, we won't get bogged down in the deep chemistry, but you need to know about something called SMIF. The disappearance of this specific chemical signature signals the exact moment oxygen permanently entered the atmosphere. It's brilliant in its simplicity.
When ultraviolet light from the sun hits sulfur dioxide in a completely oxygen-free atmosphere, it creates this SMIF signature in the rocks. But the very second you add oxygen to the air, it creates an ozone layer. That ozone blocks the UV rays, and the SMIF signature vanishes from the rock record forever. It is a perfect, undeniable binary switch. And here is where it all comes together. Work and his team found the smoking gun in ancient rock formations in northwest Russia. They were able to date the exact moment that S-Myth disappeared. But here is the absolute kicker. The physical glacial deposits, the actual rocks left behind by the Snowball Earth, sit exactly 60 meters above the point where the S-Myth signal vanishes. That placement unambiguously confirms the timeline. Oxygen definitely came first, the greenhouse methane collapsed, and the ice followed. Counter theories ruled out.
Section 5. Geological clues in stone. Okay, so we've got the chemistry, but to ground this in reality, we have to look directly at the physical destruction left behind by these glaciers.
The actual crime scene is perfectly illustrated by something called the methane diamectite. This is just a chaotic, messy mix of rock scraped together by moving ice. When you have massive ice sheets moving across the equator, they act like planetary bulldozers. They just rip up whatever is beneath them, chewing up massive chunks of rock called clasts and mashing it all together into a fine, sandy matrix.
Geochemical analysis by the Palto research team tells us an amazing story here. The makeup of these glacial deposits closely matches the banded iron formations located right beneath them. That means the ice wasn't just sitting there. It was physically scouring and chewing up the ocean floor and continental shelves. It was a violent time. But interestingly, as you move to the top of this rock layer, you suddenly start seeing volcanic elements. This is a massive clue. It strongly hints that heavy, earth-shattering volcanic activity eventually released enough CO2 to build up a brand new greenhouse effect, finally breaking the planet out of its millions of years-long ice prison.
Section 6. Aftermath of the freeze. So what exactly happens when all that ice finally melts? What did this radically transformed, newly thawed world look like? Well, following the snowball, we see the deposition of immense manganese fields. In South Africa, sitting right on top of those glacial rocks is an unmatched 50-meter thick blanket of manganese. For manganese to form chemically like this, it requires an incredibly high redox potential. Put simply, it demands a ridiculous amount of free oxygen. This proves that once the ice finally melted, those same cyanobacteria that started this whole mess were absolutely thriving. They were pumping immense, unprecedented amounts of oxygen into the newly warmed oceans. This whole scientific detective story is so perfectly summed up by this realization. An evolutionary accident, the genesis of oxygenic photosynthesis, triggered one of the world's worst climate disasters. It wasn't a giant asteroid. It wasn't a sudden shift in the sun's orbit. The evidence points directly to life itself. An evolutionary mutation essentially choked the planet on its own waste product, creating an environmental catastrophe on a scale we can barely comprehend.
And as we sit back and consider how radically early life altered Earth's ancient atmosphere, it really leaves you wondering. The Great Oxidation Event proves beyond a doubt that biology and climate are fundamentally linked, and that living organisms can literally rewrite a planet's operating system. If microscopic bacteria could accidentally trigger a global freeze that lasted millions of years, what permanent isotopic signatures and rock layers are our current climate changes going to etch into the stone of the future? Definitely something to think about. Thanks so much for joining me on this explainer, and keep your curiosity alive.